Good morning, everyone. Welcome back to Pillow Lava, and welcome back to the Rockstone Right Messy Horizons devlog. This is episode 1, not to be confused with episode 0, which was last week. Last week-ish. It's complicated, I'm busy, and also procrastinate. Um, Episode 0 was just me describing what the series is about. Episode 1 is going to be about the informal research process, which is essentially what I call the process of I want to make an art piece about something, art being any kind of art form, whether that be writing, drawing, videography. Um, now, don't count video essays in that. Video essays should be researched more thoroughly, more scientifically. This is not that. And I'll hopefully make it clear why later. Um, let's say you want to, I don't know, write a short story, or you want to make a video game, and you want to have something from the real world in that piece of art, um, a short film even, um, but you don't really understand it very well. Um, in my case, I'm actually researching a mathematical algorithm, um, because this is a programming project. But hopefully a lot of the principles should apply pretty well. Because art is one of those things, I don't know if you've thought about it much, where there's a lot of continuity between different art forms in like the process, the underlying nature, how you do it efficiently, how you do it poorly. Um, the answers to those prompts, so to speak, are often the same between different types of art forms. It's very interesting. Um, Let me open up my script real quick. So we're going to be going over the informal research process, and we're going to be going over my application of the informal research process and how far I've gotten thus far. So, just at the outset, I want to make it clear, I do not, in general, condone the use of things like large language models and what has been termed generative AI. I don't like the term AI. I don't use it unless I'm referring to something, because it's uselessly vague. Unless I'm referring to its, more traditional use in industry, which is in the case of like the program that decides where a creature in Minecraft pathfinds, right? That's called the mob's AI, because that's just an old term from many decades ago. Many decades ago. Um, so in this case, I'm talking about large language models and other kinds of generative machine learning systems, including video generation, image generation. I don't generally condone it because the training is very expensive, and the usage is very expensive. It uses a lot of water, um, and there's a bunch of other stuff that I really am not educated to talk about on. Um, However, it's a technology, and technology has use cases. And even though I personally don't think these are technologies that we should be developing, considering we could be putting this money into like research using machine learning models to figure out protein structures, and specifically protein structures in warm environments and how that changes things, and um but that doesn't mean it doesn't have use cases. And some people have found those use cases. Um, and we'll get into why that's relevant later. Um, First, we need to get to step 0 of the informal research process, which is figuring out what you do know and what are you trying to accomplish, right? In my case, I actually have a specific thing that I'm trying to do. So essentially, there is this file in the in the default Minecraft data pack called overworld.json, and there's another .json and an end.json as well. Actually, there's a few of them, because of course there is. But in this case, it is under, I think it's under dimension. It's under data slash worldgen slash dimension. Um, And in 1.21, which I believe this is 4, I think. Sorry, it's been a while since I formally worked on this project. I'm pretty sure it's for 1.21, but I could be getting that wrong. That file is a big list of these things called which I'm calling biometries. I'm pretty sure they're called biometries in the file. And essentially each of these are rectangular prisms defined by sets of ranges. If you're getting lost in the terminology, bear with me. Ultimately, they're rectangles, or technically hyperrectangles because they're higher dimensional. They're 6-dimensional to be precise. And I want to take an existing one of these files, and specifically, so essentially, you have a Cartesian plane, Cartesian grid here. Can I do? No, I cannot. You've got a Cartesian grid, and you have like one here occupying this space, one here occupying this space, and so they're just these arbitrary sets of ranges, right? So you've got this side of it and this side of it. You got this side of it and this side of it. You got upper and lower bounds in each dimension, and ideally, they perfectly fill with no overlapping this, box that's -1 to 1, 1 to -1. And so you've got these, and they fill the box, right? You've got one here, and you've got like one here, and you've got like one here. And obviously this is not perfect, not a perfect depiction of what's going on, but you get the idea, right? And they're all rectangles. They strictly are rectangles. Or in this case, hyperrectangles. Or realistically, in the more general sense, orthotopes, and we'll get into that later. And so let's say I want to add this box here. You know what? I want to add this box right here to make it more obvious to see the problem. This box is now overlapping with a bunch of other boxes. And actually, box is a technical term, kind of. It's a little overgeneral, but it has a mathematical definition that applies here. This box is now overlapping with these other boxes, and that's a problem. So what I need to do is I need to say, okay, let's create a new thing, right? Let's create create a new thing where this new box occupies this space. However, you notice that's not a good color for this. These boxes are no longer rectangles. They're no longer boxes. They've got holes taken out of them. And because of the nature of the data type, that doesn't work. So we need to somehow turn these boxes into something like, I guess it would be these boxes. And then you have this section over here that you can just delete because you don't want overlaps. We need to turn this box into these boxes. How do you generalize that to higher dimensions? Because I can't just do this by hand. This needs to happen fully automatically because I'm going to be adding dozens of new boxes, and it needs to generalize to 6 dimensions. That's not on the face of it, that's not a trivially easy process. So that's my problem, right? And my constraints are, I have this subset of a Cartesian plane. It's divided into orthotopes, and I need to be able to introduce a new orthotope, subdivide any orthotopes it's in contact with into their own orthotopes, remove any overlapping segments, and save that as a new copy of the file. And I'll warn you, I've got the algorithm written down. I'm very well prepared. However, I haven't tested it yet. I haven't proven that it's working. I will be doing extensive testing in the next devlog, hopefully. Or at least I'll be reviewing extensive testing. But so that's my problem. What's your problem, right? That is step 0, figuring out what you're even trying to solve, what you're even trying to figure out. And of course, this is a lot more technical than you're probably facing than what you're trying to do. Then you get to step 1, right? Now you actually thought about your problem a little bit. Not that you haven't, not that I'm assuming you haven't, but make sure you have. You can kind of start thinking, okay, so this is what I want, vaguely. That, in my experience, it helps you with having an intuition about what you're trying to do. Because this is research for art. Intuition is very, very powerful when researching for art. And if you're going in completely blind, it's going to be a bit more arduous. And you don't necessarily know how to pick out the things that you're looking for. Anyway, step 1 of the informal research process is figuring out how people, ideally how the experts, talk about the field you're researching. Because they use a lot of words that you've never heard before. They use words like orthotope to describe things that are very simple, very obvious, hopefully, but not necessarily, that you've just never had to describe formally, which is completely valid. We as humans living in society do not have to formalize everything all the time. As much as I might wish we did, that would make life kind of a pain for most people, and so I understand why we don't. And so there's a few ways of doing this, right? There's a few ways of doing this, and it depends on your willingness to use generative machine learning models and your time restraint and your resources available to you. Generally, they're all going to need internet access, which I presume you have because you're watching this video, but, who am I to make that assumption? Option 1, which works if you are, going to a college that has professors that work in a field similar to what you're looking at. Get expert opinions, literally, or get professional opinions, either way. Find people who know what you're looking to understand, and send them an email. I know it's a little arduous, and for my brain, it does not compute. It does not work very well, because I don't know why. I haven't gotten that deep into it. But that's option 1, right? Find people who know what you're interested in learning, send them emails, see if you can schedule, an informal, hey, let's talk about it. Let's talk about this thing I don't understand. I want to learn. They will be more than happy, hopefully, to sit down with you and teach you about the field that they love so dearly. Very easy to do if you go to an institution that actually has people in that field. Not hard to do necessarily if you don't. You probably want to look for institutions that do that, though, or that do have those people. There's other options. You can, email people at companies, you can, talk to people on the street, but I feel like that's just the most direct and effective method. Granted, it's not tried and tested, so maybe it's far worse than I'm giving it credit for. And also, don't be demanding. Respect the people's time, because, it's their choice to help you. And don't expect them to respond quickly or respond with as much enthusiasm as you have going in. They might, and if they do, excellent. There's a lot of really cool people out there doing really cool stuff. But not everyone's like that. So just be patient, give it time, don't harass people and send them a million emails. But sending 1 or 2 can be very powerful in learning about this field. The second option number 2, for learning how people talk about your field, is what I like to call recursive keyword search. Usually done in academic journals, but of course, do I still have Paint.net pulled up? I do. Well, I guess it's somewhat convenient. Which works excellently on a page like Wikipedia, because Wikipedia, like, let's just go, for example, I've been looking at brown algae a lot recently. Like, I'm like, okay, so I'm researching brown algae, and it's like, let's say I find a word that I've not heard before, but I think might be useful. I don't know, like whatever this is, fucoxanthin. What is fucoxanthin? It's a pigment, sure, but like, what's its molecular structure? Okay, cool. That's its molecular structure. And this is why it's useful. And it, I mean, to me, I look at this and I'm like, oh yeah, of course I would look brown. But that's because I do biochemistry. And of course this is like a strong antioxidant. And also, what the heck is this thing? Excuse you. Okay, that didn't work very well. More details. That's not gonna help me. This carbon double bound to two things is very uncommon. So that was a bit of a surprise for me. And the epoxide over here is a little bit cursed as well. This is the cursed molecule, if you're not into chemistry. But, like, boom, Wikipedia. Very fast, very easy. And for art, wonderful resource. So much information, pretty reliable. More often than not, of course, there's, it's not infinitely reliable, and it's got problems, and yada yada. For art, researching for art, Wikipedia, excellent, outstanding resource. There's also academic journals. There's lots and lots of academic journals out there that all focus on different types of things. And so what you do is you look up, just how you think people would describe your field, the field you're trying to research. You just kind of, you throw some words into the search bar and see what happens, and you find resources that you think might be kind of useful, or at the very least you think will talk about the things that you are interested in or that are important for what you're trying to learn. That was a long sentence. Sorry. Find a journal, find a wiki, go to Wikipedia, type in just something you think will give you a lead, right? You're looking for a lead. And then you find a source. Ideally, I forget the terminology for it, but this is where you open new tabs, right? Every single click should be a middle click. So you open the thing in a new tab, or you close an existing tab. That way you can always go back to an older part of your research and kind of take a different branch, right? Because sometimes you don't always know which branch you're supposed to be going down. And this sort of thing it's tedious and it takes time, and you'll find a lot of stuff you're not looking for. But once you've narrowed your search terms down, usually you'll find some really good resources in the end. And so this is kind of my preferred method when generative machine learning models aren't useful or are invaluable for whatever reason. And we're getting to that part. Just as a heads up, and I'll definitely emphasize this later, when you're performing recursive keyword search, what you want to do is you want to find a paper that seems vaguely, like it's vaguely talking about what you're looking for, open it in a new tab, look through the abstract, but also look at the introduction section. Because usually, with academic sources, you have this introduction which summarizes the work in the field that is relevant to that paper. And you're going to find a lot of terminology in that section. You're going to find a lot of new search terms, you're going to copy those search terms, go to a new tab, and type them in and see where they take you. And you're going to find relevant sources, and you're going to go to the introduction, you're going to find new search terms, and you're going to go to a new tab, and you're going to type them in and see where it takes you. That is why I call it recursive keyword search. It is a very powerful method, a very tedious method. Can be very confusing and frustrating at times, but it'll get you somewhere. And hopefully, without too many branches, it'll get you where you're going. And at the very least, it'll give you a lot of information about, vaguely what you're trying to learn. And that can be very valuable in and of itself, depending on the situation. Step 3, or number 3, option number 3. And this is especially viable if you don't care about the environment, or if you are pressed for time like I am. Large language models are built to understand or be able to decipher the meaning of sentences. And I say understand because large language models don't think. They do not have brains. They do not feel emotions. They are not conscious. They are not built in a way that makes them topologically capable of consciousness. Anyway, they're really good at deciphering the meaning in a sentence. That is what they are built for. And so, if you describe to a large language model, I want to find useful search terms that pertain to this field, it will find you some useful search terms. Or I want to know what this thing is called, it will tell you. Usually, it can get it wrong, and it often does, and it will give you more information than you need. But it'll find words, it'll find search terms that you can then plug into recursive keyword search. And that can expedite that process massively, especially if you're working in a field that you've never even thought about before, or hardly heard of, or, like for me, I don't do much mathematical research, and so me trying to figure out a mathematical algorithm, or how other people have implemented a mathematical algorithm, I'm going to need a good lead at some point, and large language models are good at that. So those are the main options that I personally picked out. If you've got other ideas, feel free to mention them in the comments or whatever. I'm literally not asking you for engagement. I'm telling you, I would love to hear how other people think about this process, because this is a thing that I came up with, and I probably got some stuff wrong, let's be honest. That's step 1. Understanding how people talk about your field. It's an arduous process, and it can take a long time, depending on what tools you've got access to and the like. Step 2 is actually, finding papers that are useful and relevant to your field and reading them. Yay, reading papers. Now, of course, this is going to be you are finding a paper, reading the abstract, determining from the abstract if it's even relevant to what you're trying to figure out, going to the introduction section, getting, some information. Now, I will say, this is where academic research kind of, not very helpful. Find meta-analyses, because a meta-analysis effectively summarizes, or finds trends among large numbers of papers. I'm not going to get super into it, but the objective of a meta-analysis is to determine if findings that certain papers purport to have are consistent and replicable. And those can be very powerful studies. I would also recommend finding textbooks, which are going to be a little dry more often than not. Or, I mean, if you're doing historical research, there are plenty of nonfiction, enjoyable books out there. And there's probably some on, these sorts of fields as well. They're just harder to find. I know I was looking for one recently, and while I was not looking super duper hard, I ended up just going to a bookstore, and hey, you can go to a bookstore, um, which, is going to have fiction and nonfiction and a lot of pseudoscience, but you might find what you're looking for there. No guarantees, but you might. You can always email libraries, or go to library front desks and see if they, can help you find things, and there's tons of resources out there. But find sources that actually talk about the thing you're trying to learn about. And once you have those sources, learn. It's pretty straightforward. Step 2 is just learn about the field, learn about your subject, and start piecing together what your solution is going to be. Step 3 is to write down your I'm calling it conceptual solution on paper. And exhaustively, ideally exhaustively on paper. Because if you start to implement your solution, or your, the thing you've learned, however that may manifest in this particular field, you start writing it down, or you start implementing it, and then suddenly you learn that some very important piece of it was wrong or incompatible logically with something else. So write it down on paper. Get everything out. Get a, it doesn't have to be extremely exhaustive, because again, we're not doing science here. I'll be doing science later, but you're not necessarily doing science. And make sure that it works, or make sure that it looks like it's going to work at least. Ideally you can prove, and you can follow the logic as you write, as you've, reread all the stuff you've written. And you can show, okay, yes, this makes sense. You can kind of have that reassurance that you've learned what you need to learn. And then finally, step 4 is implement the solution, whatever that looks like. And maybe that's a much longer process than even all of the previous steps have been. But that's not for me to decide. That's for you to decide. Isn't art fun? So that is the informal research process. Nothing super crazy. It's a little arduous, it's a little annoying, but when you gotta learn how to, how something works before you write about it, gotta learn somehow. So now, what did I do? How did I get through the informal research process for implementing my mathematical algorithm? I will say I got lucky, and it went pretty well, pretty fast. You might not get this lucky, and that's okay. And maybe you've got less experience reading, academic papers, and maybe you've got less experience in any or all of these pieces of the puzzle, and that's okay. It all gets easier with practice, trust me. So where do we begin? Step 0, describing the objective and constraints. I've already shown you most. Oh, I've already shown you most of my objective. I've shown you most of my objective already. Be able to insert new orthotopes into a system of existing orthotopes and subdivide those orthotopes to avoid overlap. I can actually show you what this file looks like. This is we'll get into what's going on here later. But we have the biome source, biomes, and so everything within this set of square brackets is a biome entry. If you're not very comfortable with looking at code or JSON file as a JSON file, that's okay. What's important is you've got this block here is one biome entry. It has a name, and it has these things, which are lower bound, upper bound, lower bound, upper bound, lower bound, upper bound, lower bound, upper bound, lower bound, upper bound. There's 1, 2, 3, 4, 5, and 6. And of course, some of them are not lower bound, upper bound, which I had to figure out how to handle that. But that's my problem. Point being, I need to turn these into more of these, and they all have to be this. Offset is ignored, because it's different. It's not like the other parameters. Anyway. So that's what I'm working with. These are my constraints. It has to be formatted exactly like this, in order for it to work properly. Which means that I need to divide it in a way that splits everything into lower bound, upper bound, right? But because they're all orthotopes and they're all angled, with faces, because they're 6-dimensional, the term face is kind of iffy. But you can imagine each face is a subset of a hyperplane. That doesn't make any sense to you. Don't worry about it. Those are all gonna be like either parallel or perpendicular to each other, which makes the math very easy. And this is the code. I'm not gonna stop. I'm not gonna hover over the code for too long because we're worrying about that later. Here's kind of my flow. Note there were a large handful of papers and places I went between these. But these are the kind of critical steps. These are the pieces that I would report as a source for my algorithm. First, I just have a definition of orthotope, which is very useless if you're not a mathematician. But essentially, they're rectangles. They are higher dimensional rectangles. And they're axis aligned, which just means this line, x-axis, y-axis. Boom. This 90-degree angle. This parallel. This 90-degree angle. This parallel. Okay? Okay. They're all these. All of them are one of these. You can define each with lower bound, upper bound, lower bound, upper bound, etc., etc. This is how you define that mathematically? Don't worry about it. Then I found this Stack Overflow, a thingy, what is this even called? Question, I guess. Talking about someone trying to see how you can determine if two, in this case, rectangular prisms are overlapping, if they are, whatever, like mutually parallel or whatever, if they're both axis aligned, are they overlapping with each other? And this person had a response of like, you know what? This generalizes to all dimensions, and you just have to check if, and this is very, 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 very compacted code for, is the lower bound of one beneath the upper bound of the other, or vice versa? That's what this is saying. And it's written in, I think, Java. I don't remember. It doesn't matter. The math is the same no matter what the programming language is. So, lower bound, upper bound, lower bound, if they are, if they contain each other at all, move on to the next dimension and do the same check, and move on to the next dimension. So we've got 6 dimensions to loop over. And then a special case for non-ranges for integers, or I guess it'd be floats, for scalar values. And I saw this and I was like, okay, so this is going to be one of the checks that I need to perform, right? Because I'm only going to subdivide one of the orthotopes if it is overlapping with the new orthotope. If it's not, I can just completely skip it and don't have to worry about it at all. But I need to perform that check nonetheless. And then I found this math overflow entry question thing, which talks about basically my problem, and they link to a bunch of really good leads. Or this person, what's their name? I should probably also credit this person. What's their name? Hard Math. And this person, Joseph O'Rourke. I probably butchered that. Sorry, Joseph. Lots of really good sources here. I used many of these leads on my search, and eventually, oh, this is also what introduced the search term binary space partitioning. Binary space partition or binary spatial partitioning is the act of subdividing a subset of space. So that is, when I do got a rectangle, I can literally be drawing a rectangle like this. Got a rectangle, and I'm going to cut it in half. I have performed a binary partition of the rectangle. Technically a spatial binary partition because it splits this region from this region. And there's 2 regions, so it's a binary spatial partition. It's way simpler than it sounds on the surface. So that's a search term. And eventually I found this paper, Merging BSP Trees Yields Polyhedral Set Operations. I went on a kind of a rabbit hole of set operations and stuff, because technically that's kind of what I'm doing, but that's a much more generalized version of what I had to do. And I was reading, I read the abstract, I think I read the abstract, honestly I don't remember, but I was reading the introduction and kind of got through some of this stuff, and I was like, and then it started talking about what binary space partitioning is, and how you can describe it using both the space, right? I'll describe this later, and also the fact that, boom, rectangle, binary partitioned rectangle. This half is distinct from this half. And, like, you could imagine writing, like, a little arrow here and saying, okay, this is a positive half, because math, and this is a negative half, because math, and the opposite. And so now we've divided a rectangle into 2 halves. Crazy, right? And we've said that those halves are different, but that actually is more useful than you'd think. And looking at this, I was immediately like, wait a second. Oh right, I forgot to show you. Here we are. So here's, I don't know if it's gonna show up good, but here's my kind of work on defining the problem. Defining the problem, and like, here's my work on kind of trying to get some intuition around what's going on in the problem, and then like, oh yeah, and here you can see my, I wrote down what you can see right here, this tree, and I was like, okay, so what you can do is you can imagine splitting up, you can split up the one orthotope into like a positive, negative. Let me just show you. My desk is a mess. So you split this up into like a positive and a negative. And let's say this is your other orthotope that you're adding. This is the new orthotope. And so you split this orthotope into a positive, a negative. And then one of the key pieces that I took away from this article is that, gosh, this is a difficult to describe graphic. But essentially you start with a region, you split into positive and negative, that's what this is saying. You start with this first split A, right here, that if you can see that properly. And you say, okay, everything that's not containing 1, let's say 1 is our new orthotope, just as an example. Out of the entire space, everything that's not containing 1 is the positive side, everything that does contain 1 is the negative side. And then you do split B, and as you notice, split B does not cross through split A. Split B just goes down this way. And what's important there is we're saying, okay, we're now ignoring all of the positive space to looking at only the negative space, and we are now partitioning the negative component of that first partition. And so we're doing recursive partitioning, and so first we do A, then we do B, And then from the negative section of B, which contains 1, we do C. And we've got this positive space down here and this negative space up here. And after all of that is said and done, 1 is the same thing, or the same region at least, as the overlap of all of the negative pieces. And in fact, it's only one piece. It's not really an overlap, because we threw away all this positive. We threw away all this positive. We threw away all this positive, and we're left with this one piece. It's kind of difficult to describe. But that was a revelation to me. Because it's like, okay, well now I can do... So now this positive goes somewhere. We do something with it. And out of this negative, we can perform a new partition here. And we can say, okay, well this is going to be positive because it doesn't contain n. And this area is going to be the negative, right? This whole area is going to be negative because it does contain n. And then we do one more partition here. And this is going to be the positive because it doesn't contain n. This is going to be the negative because it does contain n. And what do you know? We just derived the overlap between those two orthotopes. And because of the nature of orthotopes being a negative, or like lower bound, upper bound, lower bound, upper bound, as I was emphasizing earlier, we can say, good, new color, is this lower bound overlapping with this rectangle? If so, perform this partition. Is this bound interacting with this rectangle? If so, create this partition. Is this bound overlapping with this rectangle? No, do not perform a partition here. Is this bound overlapping with this rectangle? Yes, so perform a partition here. And that realization of, okay, I can say we have, like, the y-axis, and we have the x-axis. Got these both along the x-axis. And we've got these both along the y-axis. We'll first loop over the x-axis bounds. Lower, higher, partition, partition. And then we'll loop over the y-axis bounds. Lower, higher, don't partition, partition. And that means we now have an algorithm, right? Immediately, that is a replicable, that is a consistent way of finding every single overlap between this orthotope and the other one, and creating every single necessary partition and ending up with only the overlapping section of the original. You can just throw that away. Now, in reality, every single one of these positive segments we're actually saving to the file, and the negative section we're not. But, like, that was kind of a magical moment. I've got it written down here somewhere. I mean, it's basically just this page. And so yeah, I've literally got the algorithm written out on paper here. Is that backwards? No, it's not backwards. Okay, I've got the algorithm written here. So pick an axis, determine if lower is within bounds. If so, make the partition. Determine if higher is in the bounds. If so, make the partition. If either of them aren't, just don't make that partition. It's very simple, because of how friendly and how mathematically elegant, so to speak, the orthotope as an object is. And then here I've got this this idea of how, like, you start with your first list of biometries, and then you subdivide and you add some of these biometries into the new file, and it's a whole thing that I'm not really going to get into yet. If you want me to get into it, I can do a separate devlog. Just let me know. Tell me. I am a human being, and I think I get notified when my videos get comments. I'm supposed to be. So, like, I do listen. I think. I try to. That doesn't mean I've got the excess time to, like, respond and do stuff, but, you know. If you want me to do something, let me know. If you want an update to Roxanne Write as a mod, if you've got a feature request, let me know. I'm sorry I cannot always work on everything, but since I have time and I need to use time, just tell me. Just talk to me. Alright, back to the script. So that was the, and for the record, I meant to mention this earlier, when I was doing my, search term, stuff with ChatGPT, I used 2 prompts total to get all of the information I needed, and then I went back, and then I went into recursive keyword search. So, like, this process does not need to destroy the environment using LLMs, just for the record. Granted, it's still 2 more prompts than I wish I needed. Maybe if I had my own LLM, but, like, you know, that's really not that much better, if I'm being honest. At least I don't use water, kind of, because you'd probably be trained by someone else, so they use water. But my computer's air-cooled, which is mostly just for convenience sake. But, right, one thing that's worth noting is, let me, oop, this paper right here, has got 10 pages. I read 1.5 of them, maybe. We are researching for art, not for science. You don't need to read 10 pages. The 10 pages of stuff in here, most of that's completely useless to you because it's not written for you. You find the bits and pieces that you actually can get something out of, and you run with those. And you don't have to be precious with how you're looking for papers, as long as you know, are opening lots of new tabs, closing the tabs that are useless to you, or saving them if you think they might come back. Sometimes happens. I wrote stuff down in the booklet to get my algorithm on paper. Right, yes, and now I can actually show you this, my algorithm. I've got a class for the biome entry itself to make sure, just to, like, make calling functions really quick and easy. You can check if 2 orthotopes are overlapping with each other, and that's, it, actually. But then I've got functions for checking if individual axes are overlapping, partitioning them, which I haven't finished yet. This is actually the one piece I've yet to finish. This, plus I need to make some of these example files, that are, like, hyper simplified versions of what I'm actually going to be applying the algorithm to make sure that the algorithm's working, because I can't visualize a 6-dimensional rectangle. Come on. I can probably visualize a 4-dimensional. This is 6 dimensions. Maybe you could say, like, 5 dimensions, because depth is usually a constant rather than a range, but still. And then I've got some stuff for just, you know, changing the formatting of stuff, and it's a whole thing. But ultimately, right, you take the initial dimension.json file, you give it another file that's formatted identically, but all of this data is completely unused. It's just here because it's easy to make this file. And actually, I should show you. Well, let me do this in a relatively safe manner. If you're doing Minecraft stuff, miso.github.io, wonderful resource, especially for world gen stuff. They've got everything. Like, boom, this is the desert file for version 1.21. I want to go to 1.21.11. Boom, this is what the desert file is in that version. Super, actually, I might need to re-click desert, but you get what I mean. This is the stuff, and you can just download this, put it into your folder, You can modify it, and it'll like show you colors, and it'll autofill. It's so good, so useful. Um, and that's why I say it's easy for me to make this file, is because of miso.github.io. And this is actually, I extracted this from Rockstone Write in its current state. Um, there's a lot of entries. There's a lot of entries. The whole thing. These files are huge. Um, but this isn't about that. I mean, I guess it kind of is about that. Ish. If we ever get to actually porting this to newer and older versions, it will be. But, you know, this is the whole thing. You can read this code if you want. I'll, like, pause. It's not proprietary or anything. You saw how I derived the algorithm. I'm sorry I'm doing this in such a messy fashion, but that's just kind of how I do things, honestly. Yeah, once it's working, I do want to go over it. I do want to review it in the next devlog episode. Um, we'll see how long that takes. Sorry this is an hour long. Hopefully you found it interesting. Again, the whole point of this video documentation is to document my process, how I do things, how you might be able to do things. Yeah, I hope you have a good rest of your day. And feel free to come back next week. Hopefully I'll have another video out. No promises. No promises as per usual.